Okay, so I have two more things to do. I promised you a magic, host. So here is a magic. Space bounded. It really has nothing to do as is with pseudo randomness, even though I hope it will have, but and it initially was planned to have. But here is a question that the answer is of course not, but then the answer is yes. So say you have again the usual thing. You have a space S tape. You have your input, and you do your computation. Think of S as log n or something. Okay, like the usual. The input length is n, but then there's a twist. And the twist is the following, and it's like a really rude twist, like a really Israeli in nature. Is that, say I'm telling you, what, there is also an extra tape, we call it the catalytic tape. And it's of, it's a storage tape. It's huge compared to your tape. But, there is something there. But I'm not going to be here for a while, so you can use it. But you have to return it exactly to what it was before you come back. Does that increase your computational power? Right, so you have log n space, you have poly n more space that is initiated to something. You can touch, you can touch it, but you need to return it back. So of course you can save what you change, but then nothing happens. It could be anything. You cannot compress it. Maybe you cannot compress it. You can try, usually, but it should work for any input.
Yeah, you have to say what you change. But yes.
What?
The location of the
Amazing. No, that was my idea. No, so that's not what they use.
It's still
not very nice. It's very nice. They did it too fast. They did it took an hour to think about it. Yeah. No, so his idea, I don't want to speak because it's my idea. I'm working on it now. But the idea is that okay, so later. But what's the initial? No, actually, the idea is much more interesting. So I'm not going to tell you the idea. I'm just going to tell. What we did just now, but I did the day before, but in many more hours than you, is it's not going to. So what we did was to try to use it for storage. Like we try to benefit storage-wise from that. And the question is, and that's a delicate question, delicate difference. I don't want to benefit in storage. I don't want to increase my computational power. So if you get a bit more randomness from that, it won't help you. It will help you, but not depending on what extent. So it turns out that using that, I can actually show you a bit of it how. You cannot do just L, you can do like NL in this thing. And actually, even if you like these things, you can do TC1. Like every non-deterministic computation in log space, you can do with this. Crazy. How? Good. So the TC1 is right. You have like a log depth threshold circuits. It's stronger than it. I always forgetting those things, but I should start knowing them. But let me tell you just the gist of it. It has nothing to do with that, but it's so cool. The gist of it is that you can do computation in the presence of information. It's like crazy. So let me show you a very simple example. And I hope, first of all, I hope I'm able to do it because I know it's for 2 days. And one of those days I prepared the 2 hours of this lecture. And but I hope it will actually convey this. It looks so like innocent, but it's the same thing. So here is a question, an easier question. Forget about Turing machine. Say you have 2 numbers on your input, x and y. Say field elements or whatever. Don't worry about it. Just 2 numbers. And you have 3 registers. So instead of working with the usual like Turing machine, let's actually look at memory cells. You have 3 registers, and they can store FQ elements. Now, following this kind of idea, they actually are initiated with values which you cannot erase. Actually, let me call this like that. T0, and that's also O for T output, so it's a nice coincidence. T1 and T2, and they are initiated with values. And what I want you to do is I want you that, at the end of the day, I want the product of x and y to appear here, but I don't want to kind of destroy tau 0. So I want, the computation in this form. So I want x times y to be summed to what was written here, particular if I know what's here, I know how to do that. But of course, this should be the same. This should stay as is at the end of the process. In between you can erase, and that's kind of similar to what's going on here, right? You can use the extra memory. I mean, you have no other cells. You can't just multiply X and Y. You need to do it in the registers. In the registers, you can add register and then multiply registers, but you can't do it in the air.
There's like a different description.
So, okay.
Like sorry.
כן, נכון, it's similar, it's like an interface. Alright, so the way you do it is, I think some of you are just starting to do it, is, okay, the first thing I'm going to add, I'm going to kind of sketch it. I'm going to add X here and Y here. And then I'm going to take their product and add it to here. Right, so I'm going to take the product, that's something that is valid. So after that, you're going to have tau 0 plus tau 1 X, plus X, plus tau 2 plus Y. And which is like, you know, what you want.
Oh.
Right, because it's kind of there, right? So you can't avoid the taus. So you have what you want at the end. Let's call it R for W for want, or R for רוצה. The better name. And then you have like tau, but you have the junk. You have tau 1 Y, you have tau 2 X, and you have tau 1 tau 2, which kind of obfuscate what you want to look at. But then you clean it up, right? You remove those, you remove this A, subtract it, multiply that and subtract it from that from that. So you subtract the product of these from this expression. So you get rid of this and from that. And then you add X and remove the Y and subtract. You can do that, right? You have X and Y. And you can subtract the product. So you got rid of this, but unfortunately, like an inclusion-exclusion, you got this subtracted twice. But then erase X and add them back. Right, so you did computation in presence of information. And that's essentially the only technique essentially you need to do the more general test. Kind of crazy.
We have X and Y like read-only memory on this example.
Right. Usually it's something that actually comes from recursion or something. But yes, you have X and Y isolated, say in the input tape. Right. Yes.
You can multiply the first y1 plus x equals y.
Yes.
You can multiply and just add it.
Yeah, that's a fair thing you can do. Because it's there. If you erase it and put X here, you can't restore the information. You can like the things you can do is you can take it from input to memory and work in memory. You can't work in the input tape, it's read only. I can't multiply X and Y. Right. Right, so I'm adding that. These are always there, so I can add and subtract all the time. So I can add, and then like in 2 steps. So the instructions in the registers, you can do like multiply those into a third one. That's allowed. In the registers, not in here. And the point is that when you get a circuit, actually, this is X and this is Y. So you don't really have them as input. It's recursive. It's kind of, you compute them recursively. And with just 3 bits of memory, you can compute the next value. You don't have to save all the bits all the time. Yeah, anyhow, it's I didn't mean to look at it so, but
Isn't this a breakthrough of like
yeah,
completing recursion nodes? Like this, when you do recursions, you can use all
right. Yeah, that's a very new paper that happened just now. I mean, that's like from 10 years ago, and it was crazy back then. That is like that's essentially like a reinterpretation of Barrington's theorem. Like Barrington's theorem tells you that in weight 5 you can branch a program, you can do something. It actually uses non-solvability of groups, but never mind that. And that's a simpler version. We have 8 like 3 bits, so 8. It's easier to show and requires more bits. And now, like maybe 2 months ago, there was a paper published, maybe more, but now it was accepted to stock. breakthrough that solves what's called tree evaluation problem in log space. It kind of, many conjectures are now disproven, and some conjectures are that people wanted to separate P from L will now try to actually do much harder stuff. I mean, a lot of things have shifted because of that paper, and it's as a positive thing, I would say it's very simple. Yeah, it was the candidate, and you can do it in log n, log n. Crazy. Yeah, but come on. Look, I mean, no, okay. So compared to what? So it was log square of n, the trivial thing, and then the same, I think, same two people did log square of n over log n, and now it's log n, log n.
So what does it show in the harder problem? Shows we can represent any.
So the actual problem?
Yeah, like if we have use like an arbitrary and the bytes or something like that.
Yes. So for example, in the particular paper that I'm talking about now, which is actually easier to to explain than that, not just the result, is that say you have like a depth h, and that's very similar to what happened in Nissan. So what I'm going to say now gives hope for something to happen also in space bounded. Say you have depth h, tree, you have the leaves at the bottom with the values, whatever, I don't know how many, 2 to the h, okay? And then every gate takes 2 inputs, everything is in FQ. It takes 2 inputs, and it computes some function from FQ times FQ to FQ, and you kind of proceed like that in recursive way. The general agreement between everyone, besides the 2 people in this paper, is that if you do that, then the space that you need, I mean, what's the space? You're going to have like you do in left, you do in right, and so forth. I mean, that's the only thing you can do. It's not, but the only thing you can do is do left and right. And when you do left, you need to save like log q, the field element, log q bits of space, to save that while you compute that. So and this goes recursively. So the conjecture was that you need this number of space, this space complexity to compute that. This disproves that it essentially does that times log q. It's crazy. It turns out that when you move to compute the right thing, you can use the space here for the time being, because you won't need it until you reach here. So you can reuse this space not for storage, so not for compression, but actually that's a good idea. I'm happy with it. Good, very good. Not for storage, but for computation.
So actually, like you use the registers for working time,
right?
But it doesn't cost you anything.
Yes.
That's the idea, because like as
yes.
you suggested, like we couldn't compute the x and y
right.
Physically because otherwise it would be like another cell.
Right, exactly. So x and y are like x and y are like here. So you have the information stored, you have x and y. You always anyhow, it's more complicated, but yeah. Yeah, okay. You need 3 registers, not 2. You need 3, but with 3 you can do it. You don't need to have like h of them, just 3 of them. It's really groundbreaking. Like it's also completely non-intuitive, I think. I don't know.
Yeah. So the problem here is like general recursion?
Actually you can, right, yeah, essentially. I mean, here it's for a specific case when you compute functions and so forth, but generally, right, for recursion, when you have something in stack, you can use like you same thing on stack, and the common knowledge is like, don't touch the stack. No, I do touch the stack. Don't worry about it. You can kind of invert it. It's kind of reversible computation. You can compute it back. Fantastic. It's like 2-page proof, by the way. Amazing. Steve Cook, like the father of and Levine, but like spent the last 10 years trying to solve that, and then his son and another guy, Ian Mertz, they solved it, and he gave him $100 for that because he promised. Right. So I'm not quite. I mean, that was known. I mean, this thing, right? And definitely the catalyst was known also. But there was a jump from that to that, which I can't say I really understand. So I don't understand. It's just me. It's not like the paper. The paper is everyone. It's just me that don't understand why can you just take these techniques and make it work. They do something more subtle. Yeah, a little bit more subtle. Like they break down. Maybe that's the point. Probably that's the point. That's what I'm missing. But they really break down this thing to a polynomial. So they think of it as like not field elements, but you have low Q or two low Q bits input and a low Q bit output. So they work over F2 really with many input and outputs. I'm not exactly sure why. Initially I thought it's because they don't like FQ. It's, like people that like bits, but complexity people. But now I'm not sure anymore. And the point is that using if you take a field extension of F2, then you can use a primitive root of unity to kind of, and the simplest thing that you know, that their sum is like 1, or depending how you do it. So here, the sum is 1, to kind of juggle the information in a certain way. Very similar to what happened here. Like here we juggled it explicitly on the board. There is a formula for doing that. You don't need the formula, but there is a formula for doing it.
Anyone check the
I don't know. It's really, really new.
also general, it wasn't that
Yeah. No, it is. It is.
Can you improve it? You can't improve the age somehow?
So it should be H plus log Q. So there are low bounds, and now they get times log Q. I think only on one of them, I'm not sure. Maybe Tomer remembers. But yeah, the point now is that I mean, I think that's groundbreaking enough, but it would be nice to get rid of that also. Yes. But let's move to some other stuff. I mean,